Hey guys, hi. So today we are going to try to solve some genetic problems involving the genotype. So here's a beautiful question. Purple kernel are dominant over yellow. So we know purple. So since they are dominant, I'm going to represent them by big P and big Y. In corn, also full kernel are dominant over shrunken. So big F and small f. Right? Shrunken is small f. A cross was performed between corns with purple full kernels and yellow shrunken kernels. The result was given as purple full, purple shrunken. So this is the observed phenotypes, right? Now the question says, what do you think can be the genotype of the parents in the progeny? Perform a chi-square test. So there are two parts of the problem. First, figuring out the genotype, and then you have to justify if your calculations, if your assumption was correct. So what I'm going to do is I'm going to separate them out. Okay, so let's do that. So as you can see, if I calculate all the purple, that comes around to be 215, and all the yellow, that comes around to be 185. I'm going to do the same with by grouping the full together, 112 plus 91, and by grouping the shrunken together, that's 103 and 94. Now it looks like that the ratio big P upon small p, now here I am just talking about the phenotype, not the genotype, but basically purple upon yellow equals 1:1, and the similar thing appears for the full and shrunken, again a ratio of 1:1. So let's solve for them. In what cases that you get the ratio 1:1? So when you have the parents to be, let's say, heterozygous crossed with homozygous, because yellow means it has to be homozygous, right? So if you make this cross, what do you get? Big P, small p, big P, small p, small p, small p, small p, small p. So you get around 1:1 ratio. Now let's talk about the full and shrunken. Again, same 1:1 ratio is there. So again, you can imagine that here perhaps the parents, one of the parents are heterozygous and one of the parent is homozygous, right? Now what I've done is I have combined. So big P, small p, small p, small p, big F, small f, small f, small f. So one of the parent in both the cases, because the cross was performed between purple and full kernels. So remember, the dominant phenotype is expressed both as a heterogamous, in a heterogamous condition, or a heterozygous condition or a homozygous condition. So that is why we can assume that this is big P, small p, and big F, small f cross small p, small p, small f, small f. Now that says that the ratio of the four progeny, let us try to write their phenotypes now. So big P, small p, big F, small f, that is what our first phenotype was, right? So I'm going to write the phenotypes here. So purple and full, big P, small p, big F, small f. Purple and shrunken, big P, small p, small f, small f. Yellow and full, small p, full is big F, small f. Yellow and shrunken, small p, small f, right? So the thing is, because of this ratio, they should all have been 100. That means this is your expected value and this is your observed value. Now I want to remind you that we have already solved the first part of the problem. What was the first part? The genotype of the parents, the configuration of alleles of the parents. They are heterozygous. One parent is heterozygous, one parent is homozygous, right? So this is the parent with purple full kernel, and this is the parent with yellow and shrunken kernels. And what are the progeny? What is the genotype of our given phenotypes? That's clear to us. Now we must make sure that what our assumption is, that is statistically correct. So we have written expected and observed, right? Now how do you find out if it's correct? So first of all, you find the chi-square test. How do you find the chi-square test? That is observed, summation of observed minus expected, the whole square, upon the expected value, right? So we have observed, we have expected. Let's find out. So O minus E, that's 112 minus 100, that's 12, that's 3, that's minus 9 and minus 6. Now you have to calculate O minus E, the whole square. So that's 144, that's 9, that's 81, and that is 36. Now let's not forget to divide them by 100. Okay, so I'm adding this by divide to this same table. So upon 100 upon 100 upon 100, right? So this comes out to be 1.44, 0.09, 0.81, 0.36, right? Now this is summation, right? So this comes to be, if you do the math, around 2.70. Now what were the four categories here? 1, 2, 3, 4. So first of all, we have to calculate degree of freedom. What is degree of freedom? That is n minus 1. What is n here? The number of categories. So that means 4 minus 1, that equals 3. So now we have to look at the chi-square table. Okay, so there's a standard chi-square table. We have to look at the chi-square table. So you can, as you can see in this table, we have rows and we have columns. So let me just place it slightly here. Okay, so what you see here, we have rows and we have columns, and what happens is this is degree of freedom we are talking about. Okay, so our degree of freedom was 3, and we have to look that for degree of freedom, our value, what was our value here? Now let us remove this, and 2.70, right? So where does our 2.70 value lies in third? As you can see, it's right here, right? 2.36. So 2.7 will be the value between this. Now what is the probability here? 0.5 to 0.1. Okay, so our calculated chi-square value lies between the probability of 0.5 and 0.1. What does that mean? That means the difference between what we observed and what we expected due to chance, the probability of that is high enough. Okay, so we conclude, right? So now we can conclude that our assumption, our genotype evaluation, the evaluation that we did, that one of the parent must be heterozygous for both the conditions and the other parent must be homozygous for the recessive condition. Our assumption, our conclusion is that we were correct, right? So we were correct. And what is the probability that the difference that we are observing is due to chance? That is between 0.5 to 0.1. Okay, now one thing is important, that generally scientists pick up 0.05 as a cutoff mark. Now what does that mean? That means the probability that what difference that you observe is due to chance is around 95%. Okay, so generally this is a cutoff, but in this example that was that. Now let us try to practice using the same. So in P, tall height and yellow seeds are dominant. In a cross between tall P with yellow seeds and dwarf P with green seeds, the following result was obtained. So this is the result. Now, again, you have to do the same thing. You have to first figure out the genotype of the parents and the progeny and perform a chi-square test to find out if your assumption is correct or not. Try to use 0.05 as the cutoff mark for this solution. I hope you really understood. I'll leave the answer for this down in the description.
We hope this video was helpful. To see more biology topics covered, click on our channel and don't forget to subscribe.